Okay, so recall that last time we wanted to solve, uh, well, we wanted to integrate this rational function. And we used the method of partial fractions to rewrite the rational function. And so I'm going to just sort of quickly go through the steps that we already covered that you should have down in your notes. And of course, it's in the last recording as well that we did, the last lecture. So the bottom of the rational function could be factored. X cubed plus 4x could be factored into x, and x times x squared plus 4. And so therefore, that made this, well, this product in the denominator consisted of a linear factor, x, and a quadratic factor, x squared plus 4. And so when we did the partial fraction expansion right here, we expanded the rational function as the sum of two fractions. The first one being a over x, because x is of degree 1, we put a constant, then one constant is one less degree than x. Okay, x is of degree 1 as a polynomial, and the constant a is of 0 degree. And then the x squared plus 4, that's a second degree polynomial. So above that x squared plus 4 in that fraction, we put b times x plus c. And so what we do then is we multiply both sides of this, and we did this in the last class. We multiply both sides of this rational equation by the least common denominator, x times x squared plus 4. And by doing that, that gave us this equation, and we got rid of the fractions. And then we have to solve for a, b, and c. Well, by rewriting the right-hand side of the equation, okay, by just distributing the a and the x and writing out the terms, we can re-express the right-hand side as a plus b times x squared plus c times x plus 4 times a. But remember, if 2x squared minus x plus 4 is to equal the right-hand side here, that means then that the coefficients of x squared, x, and the constant have to be the same. So therefore, let me just see here. Therefore, a plus b, that's in front of x squared term on the right side, that would have to equal 2. C times x on the right side, c would have to equal -1, which is the coefficient of x on the left side. And then the 4a would have to equal 4. And so you get 3 equations and 3 unknowns, and you solve for those equations. And we did that. We solved for a, b, and c. And so this allowed us then to get to the step that we got to here, where the integral of the rational function equals the integral of 1 over x, that 1 was the a that we found, plus the 1x minus 1 over x squared plus 4. So the 1 in front of the x is the coefficient b, and the -1 is the coefficient c. And so this is where we left off, right here. And of course, the so now you're continuing your notes from this step right here. Okay, that's where you're continuing your notes from. What's the antiderivative of the integral? What's the antiderivative of 1 over x?
The absolute value of ln of x.
That's correct. The log of the absolute value of x. That's right, Justice. Good, good. So the first antiderivative is easy.
8.
Now the second antiderivative, the antiderivative of x minus 1 over x squared plus 4, what we need to do is we need to split that up, that integral up. And that's what I do. X minus 1 over x squared plus 4 can be written as x over x squared plus 4 minus 1 over x squared plus 4. Okay, we can certainly do that. I mean, usually what we like to do is take two fractions with a common denominator and combine the fractions. But now we're doing the reverse. We're taking a single fraction here, the x minus 1 over x squared plus 4, and writing it as the difference here of these two fractions. But it's going to be helpful because that's what we're going to need to do to resolve the, to get the question answered. We need to do that. Okay, I'll give you a moment to copy that down. Okay, so this is where we're at. This is where we're at. And the first integral, of course, we know we can get the antiderivative. We know the antiderivative is the log of the absolute value of x for the first integral. How would we integrate the second integral? How would we integrate that? That's right, Rodrigo. We would use a substitution there. There, we would let u equal x squared plus 4. That's what we would do. Now, the third integral, there is a formula that the textbook gives you to handle the third integral. Okay, there is a formula that the textbook gives you, and you'll need to memorize that formula. But what I'll do is I'll go to the next page, and you can see the formula. But are there any questions so far here? Okay, Tina's good. Thank you. All right, well then let's move to the next page. So the substitution in the second integral is u equals x squared plus 4. And, you just go through the steps and work out the substitution. The third integral, there's a formula in the book. It says the integral, let's see if I can use the little box here. That'll work. The integral of 1 over x squared plus a squared, that's an a, not a 9. The integral of 1 over x squared plus 1 over x squared plus a squared dx is equal to 1 over a times the arctangent of x over a plus a constant. Now, the formula is general. What you're used to seeing, of course, is you're used to seeing the antiderivative of 1 over x squared plus 1. And you recognize that as the arctangent of x plus a constant. But that antiderivative is a special case of this Formula 1, because what is a equal to there? Well, the 1 can be expressed as 1 squared. So if you put a equals 1, wherever the a is, you'll get that antiderivative. But of course, we have the integral of 1 over x squared plus 4. We have a 4 here, not a 1. And 4 is equal to 2 squared. So we need the general formula. So this formula here you should memorize. And so now the integral, okay, now when I work out the integral, this is going to be my answer. The antiderivative, or the integral, of this rational function is equal to the log of the absolute value of x plus 1/2 times the log of the absolute value of u minus 1/2 times the arctangent of x over 2 plus a constant. Okay, are there any questions? All right, well, would WebAssign accept this answer as it is right now? Okay, people are saying no. Why not? What's the little issue? That's right. We have to substitute. That's right, Tina and Michael. We have to substitute the u back in there. That's right, Cologne. We have to put u back in. Well, okay, u was equal to x squared plus 4. Okay, and so our integral is equal to this here. All right. Now, do we need the absolute value around x squared plus 4, or can we drop the absolute value? Why can we drop it, Tina? Why can we drop those absolute values? You're right. WebAssign would accept that answer, but that's right. Tina and Rodrigo and Cologne were right. X squared plus 4 is always positive. And so, this is your final answer. Okay, give you a moment to copy it down. 4. Yeah. Okay. 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 Are there any questions at all? All right. So this is called, we used a partial fraction expansion. A partial fraction expansion. Okay, now what I want to do, I want to bring up the ebook just for a moment. So let me do that. We're going to do another partial fraction expansion problem, but I want to show you something here. Okay, so okay, I'm in the ebook, and of course, Chapter 5, integrals. We were doing section 5.7, additional techniques of integration. And there's the partial fractions. The appendix in the book, the appendix in your ebook, has also a section on partial fractions. So let me see if I can, let's see, I have to get out of here. Let me see. I want to get back to the home page here. So let me see here. Where do we want to? You understand what I want? I want to get back to where the table of contents is. So where would that? Hold on. Somebody has a comment here. Press. Let's see. Colum says drop. Right. Press the X on the right of the line with 5. Okay. Integrals. So let me see. All right. Hang on. Near the top. Oh. Okay. I see it. Thank you. Thank you, Colum. Okay. All right, so back in here now, you see here appendices. If I click on appendices, this book, and I think some of you might be aware of this, but there are, if I click there are different appendices. Like one is on trigonometry. If you need to review your trigonometry, you can click on the trigonometry appendix. Okay, if you click on that, it'll give a nice review of trigonometry and the unit circle and all that good stuff. You know, there are those triangles that I'm always talking about. You know, the 45, 45, 90, the 30, 60, 90. Okay. And also in the appendix here, hold on, let me just click on this. They have a section on an appendix G, integration of rational functions by partial fractions. Okay. Integration of rational functions by partial fractions. And the book goes through, there's quite a different number of partial fraction expansions that can be done. Okay, quite a bit of different ones. And I don't want to go into detail here, but I'm going to do another one with you, just so that you get you get some variety. Once you've done 2 or 3 different kinds of expansions, you're going to be okay. Like for instance, let me just ask you this here. Let me bring up the whiteboard here. Suppose that you had, you know, let's just, it doesn't, like, you know, let's say you had, like, you know, x squared. Well, I want to be a little bit careful here. Yeah, let's say you had x squared plus 2x plus 4 on the top. And on the denominator, you had x squared plus 1 times x squared minus 3. Okay, something like that. Just give me one moment here. Hold on. Let me just check one thing here. I was checking one thing. Yeah, something simple like that. If you do the partial fraction expansion, you know that one of the fractions is going to have an x squared plus 1 in the denominator, and the other fraction is going to have an x squared minus 3 in the denominator. And you notice that these factors are not repeated. These are not repeated factors, okay? They are different factors. That's important. So my question is then, above the x squared plus 1, what's going to go above there? What's going to go above x squared plus 1? Is it going to be a? Or is it going to be a little bit more? What do you think? Let's think on it for a moment. It's going to be more. Yes, it's going to be ax plus b. That's right, Rodrigo. So Michael was on the right track, but you see, since you have a quadratic factor, x squared plus 1 in the denominator, you have to have a linear factor, ax plus b, in the numerator. Now, what's going to go above x squared minus 3? What factor would go there? Okay. Good, Rodrigo. It's going to be cx plus d. We can't use ax plus b again because we need to use different letters. Okay. All right, and so that's your partial fraction expansion. And then when you multiply both sides, what's the least common denominator going to be that you multiply by? What's the LCD? What's the LCD for this problem? That's right, Candy. That's right, Alan. It's going to be x squared plus 1 times x squared minus 3. Of course, we have to put it on the left side also, so I'm sorry I have very little room here, but we know we're going to multiply by x squared plus 1 times x squared minus 3. Obviously, on an exam or in your work, you'd write it a little bit, differently. But that's what we do to both sides. And then, we're going to get some simplification. We would get x squared plus 2x plus 4 equals, okay, ax plus b times something plus cx plus d times something. So I'm not going to work this out completely, but what's going to be what's going to go in this spot here? What's going to go there?
X squared minus 3.
That's right, not now. What's going to go in this spot here? In the second spot?
X squared plus 1.
That's right, Henry. And then what you have to do is expand out the right side, and you'll get equations for A, B, C, and D. And you'll have 4 equations and 4 unknowns. And hopefully, a couple of them will be easy to solve. Okay? And, once you know a couple of the values, then it's easy to get the others. Okay? So I just wondered, are there any questions on this? Before we get to our next example? Okay, all right. Well, let us then go to our next example, if there are no questions. Okay, back to the file here. Okay, let's do this integral here. I'll give you a moment to copy it down. Okay, so here we are. All right, so look at this integral now. Look at this integral. And one thing that's of notice, that's of interest, is that this integral, hold on here, let me just, okay, they heard you, Kurt, Elsie heard you. All right, sorry. So, try to have a quiet environment, but it doesn't always, well, All right, so what's the degree of both the numerator and denominator of this rational function? That's right, Rodrigo. The degree is 3. And when that happens, you have to divide before you can think about a partial fraction expansion. you have to divide the top polynomial by the bottom polynomial. How many of you remember dividing polynomials by polynomials, maybe in pre-calculus? Maybe you did a little bit of that. Like when you studied rational functions, if the asymptotes were horizontal or oblique, or okay, Felicity knows what I'm talking about. You would have seen it. Okay, well, we're going to divide the numerator polynomial by the denominator polynomial. So let me move to the solution here. And of course, we have our limits 3 and 4. We're not worried about those right yet. Let's go to the solution. And what I'm doing here is I'm making, before I do the division, I write down, I always try to relate complicated things to easier things. Because it helps when I have to understand sort of a complicated, I don't want to say complicated, but I mean, I think dividing a polynomial by a polynomial is harder than dividing a number by a number. But the process is the same, it's division. So what I've written here is, what if we had 20 thirds? That's a fraction too. Just like, you know, just like x cubed minus 2x squared minus 4 over x cubed minus 2x squared is a fraction. Okay? If I divide 20 by 3, 3 goes into 26 times. 6 times 3 is 18. You get a remainder of 2. So 20 thirds will equal 6 plus 2 thirds. Okay, that's something that you have known for a long time, right? How to divide. Well, the same process works with our rational function. The numerator is x cubed minus 2x squared plus 0x minus 4. I put a 0x in there, so I have a placeholder for the x term. So, you know, just like 20 thirds, 20 goes, the numerator goes in the box. My polynomial in the numerator goes in the box when I divide. And then the denominator, x cubed minus 2x squared, goes outside the box. So it's just like dividing a number by a number. So I got to figure out, okay, the leading term is x cubed in both of these polynomials. X cubed goes into x cubed once. Goes in there once. Okay, well, just like when I divided 20 by 3, I went 6 times 3. You know, 3 went into 26 times, and I said, okay, 6 times 3 is 18, and that was what I'm going to subtract from 20. I'm gonna take 1 times x cubed minus 2x squared and subtract that from my numerator polynomial. And you're going to get cancellations. X cubes cancel, and the 2x squareds cancel. We get a remainder negative 4. Okay. Are there any questions on this process here? How many of you was it helpful to see like the 20 thirds example before you did a polynomial by a polynomial? I got it. Okay, good, Candy. That was good. Snega, excellent, excellent. It's just to show you there's no difference between the processes. You know. Okay, well, this means then that our integral, well, I want to say it the right way. Let me actually write this in. There's a step I want to put in here. So maybe I'll put it in red. So x cubed minus 2x squared minus 4 divided by x cubed minus 2x squared. That's going to equal 1, okay, minus 4 all over x cubed minus 2x squared. Okay. Just like 20/3 was equal to 6 plus 2/3, we have that x cubed minus 2x squared minus 4 divided by x cubed minus 2x squared. That's going to equal 1 minus 4 over x cubed minus 2x squared. It's the same process. Okay, are there any questions on that? All right. Well, this means then, thank you, Eric. We're good? All right. Well, this means then our integral here can be re-expressed as this integral. The limits are still 3 and 4, of course. But this enables us to do the problem, this step. It's absolutely amazing. The integral of difference of two functions equals the difference of the integrals. And this gets us to here. Yes, one moment. Let me. How's that? Is that all right? Assume it is. All right. Are there any questions? All right. So, I mean, we should be kind of happy here. We have the first integral is easy to do. How are we going to have to handle the second integral? What procedure are we going to have to use to compute the integral from 3 to 4 of 4 over x cubed minus 2x squared dx? How are we going to handle this second integral? We can't use substitution. Can't use integration by parts. Okay, I like what Rodrigo's saying. We could use partial fraction expansion on it. Okay, we can do that. So I'll move to the next page. Is everybody good? before I go to the next page. Again, I ask frequently because if I were in the classroom, thank you. If I were in the classroom, I could see the students copying down the notes, and I would know when to move forward. But since I can't see you copying the notes down, I have to verbally ask more, but that's fine. Okay, so this 4 divided by x cubed minus 2x squared. Hey, what do we want to do with the denominator there, x cubed minus 2x squared? What do we definitely want to do with that denominator if we're going to use partial fractions? That's right, Tyreek. We want to factor it. So, okay, let's go to the next page. Okay, I'll give you a moment to copy this. Okay, so here now, the thing is, the denominator, the greatest common factor between the x cubed and the 2x squared is x squared. But we have to write out the denominator here in completely factored form. So x squared is equal to x times x. But what happened here is we have 3 linear factors, but we have what's called a repeated linear factor. And it's important, we didn't see that in the last problem we did, but we're seeing it now, and it's important to talk about it. It's talked about more. It's talked about in the appendix, that appendix G, where they have partial fractions. Appendix G. That's where repeated factors are talked about. There, but it complements section 5.7. So what do we do when we have a repeated linear factor? Here's how you have to do the expansion. You have to write the, let's see, not Nell, you're good?
I had a quick question.
Sure.
How come we got an x squared for b?
Yes, okay, there is a reason for this. You agree that we need an A, B, and a C,
Yeah.
right? If we just had an x, if we had A over x plus B over x, which intuitively you might think to do, to put B over x and not have the squared there, plus C over x minus 2. The problem with that is that A over x plus B over x is just going to give you one constant over x. So you can combine these two fractions. And so you need to have 3 variables, A, B, and C, to solve for. And so you have to have basically independence between the terms. Well, the way you get the independence is you put the B over x squared. Now, right, x squared is a quadratic, right? It's of degree 2, Normally, we wouldn't put a constant b above x squared. But when you have repeated linear factors, that's what you have to do. And suppose for instance, you had something like 5 over x times x times x. Let's say that were your, let's say, that you have x cubed on the bottom, 5 over x cubed. If you had that, that's going to be a over what? A over x plus b. Again, so in this little side note I'm talking about, you have 3 repeated linear factors, 3 repeated factors. Okay, so when you do your expansion, you're going to have a over x plus b over, what's going to be under the b?
Squared, x squared.
X squared, right, plus c over x cubed. That's right, Rodrigo. You see?
Okay.
That's how these linear factor issues work. Okay. And intuitively, it makes sense that we would have to do something like that, because if we didn't, we wouldn't be able to solve for A, B, and C uniquely.
Okay, I see. Okay.
All right. Good. Good. So I always try to, the book will, in the appendix, will give like formulas, but if you just understand intuitively the process, then you don't need to memorize all the formulas. You'll just know what the expansion would be. So this means then that the 4 over x cubed minus 2x squared will equal a over x plus b over x squared plus c times x minus 2. And then, of course, we have to multiply both sides of this rational equation by the least common denominator, which would be, of course, x squared times x minus 2. X squared times x minus 2. And that will then reduce the rational equation to this equation here. 4 will equal a times x minus 2 plus b times x minus 2 plus c times x squared. Okay, are there any questions up to here? Okay. Are we ready for the next page? Okay. Okay, very good, Tina. All right. Well, let's head on over to the next page. Thank you, everyone. And now we continue. So the first equation is what we had on the previous page. And then I'm going to distribute the ax and the b. And then I'm going to group like terms together. Ax squared plus cx squared could be expressed as a plus c times x squared. And then negative 2ax plus bx could be expressed as negative 2a plus b times x. And then finally, you have the negative 2b. We just put that there. And on the left side, the 4 could be thought of as 0x squared plus 0 times x plus 4. Okay. This means that a plus c would equal 0. Negative 2a plus b would equal 0. And negative 2b would equal 4. And you solve the equations. Okay, give you a moment to copy that down. Okay. So now that we solved for A, B, and C, we can rewrite that second integral in this form. A was negative 1. That was over the x. B is negative 2. And then C equals 1. These partial fractions come up in differential equations a lot when we're solving what are called, we're solving differential equations. If we solve differential equations with Laplace transforms, and you'll see that in Math 282, differential equations, you'll do a lot of partial fraction expansions. How many of you have to take differential equations, Math 282? I'm sure some of you do. All right. Eric and Adriana, Esther, Dan. Tina says not me, but you never know. Cameron. Sometimes we get students that don't take Math 282, and then they graduate, but then they come back to Montgomery College because they suddenly have to take it. Maybe like if they want to go to graduate school or something, you know. But okay. So now I think are we happy at this stage here? Are we happy here? Can we integrate this?
Do we always set like it to 0? Like, because you set a plus c equals to 0, do we always set it equals to 0 when we
Well,
start off?
it's a good question, Tyreek. It depends what we have on the left side. You see, a plus c is, hold on, let me just make that. Okay, so a plus c is the coefficient of x squared. So what you're doing is you're saying that I want 4 to be equal to all this right side here. The polynomial on the right must equal 4. Well, that means the polynomial on the right, you can't have an x squared term, so a plus c has to be 0. You can't have an x term, so negative 2a plus b would have to be 0. And then negative 2b would have, that constant would have to then be equal to 4. It relates to relating the coefficients of your terms to what you have on the left side. Does that make reasonable sense? Are you?
Yeah.
So it just depends. It depends. All right, good question. Good question. Are there any other good questions? Okay, well then let's move on, because we can solve this. We can solve this. So this is going to be now, well, remember, we have, I'll go back to that. We have the integral, we have, you know, that one integral to the left, and then we have the integral of a difference of 3 functions, or, you know, it's the integral of a sum of 3 functions. I mean, we could, you know, put a plus here, right, if we want. The integral of the sum of 3 functions is the sum of the 3 integrals. So we end up with this expression here. And we can get antiderivatives for all 4 integrals. And then it's just a matter of computation. So let me give you, I'll give you a chance to copy that down. I don't think there's really anything I need to go in great detail about. The fourth integral, the antiderivative of 1 over x minus 2. So you could use a substitution on that and let u equal x minus 2. But I happen to know that the log of the absolute value of x minus 2 is the antiderivative of 1 over x minus 2. Because if I differentiate the log of absolute value of x minus 2, I'm going to get 1 over x minus 2, the derivative of x minus 2, which is 1. Yeah. All right, so go ahead and copy that down. Okay, are there any questions at all in regards to the final answer here? Let's see, Surfiel, for negative 1/3 plus, well, that we just had into right since. Let me see here. Surfiel is wondering, okay, he's pointing here. Yes, well, negative 1/4 plus 1/3, that's right. And negative 1/4 is the same as negative 3/12, and plus 1/3 is the same as 4/12. So I get a common denominator, and that gives me 1/12. So yes, you're subtracting the negative 1/3 here, so you're taking negative 4 then plus 1/3. That's correct. All right, are there any other good questions? How many are kind of liking partial fractions, partial fraction expansions? Uh-oh, Tina's not a fan, but next week you might be. Cameron, oh my goodness, 2 people. Oh, okay, thank you, Noah. Tyreek doesn't, all right, oh my goodness. Tobias, no, but Noah's a thumbs up. Kahindi's a no, oh my goodness. All right, well, I can tell you, Sniga kind of likes it, that's good. They are important for your future. They come up in differential equations, so everything you're learning, there's a purpose for it. All right, let me stop the recording here.